Hello everyone. So this is the second video in our series, and today we're going to focus on what are known as chance constraints. And so in the first video we looked at the basics of covariance steering. Hopefully everything I said made somewhat sense. You can't really draw a straight line right now, but that's okay. There we go, that's good enough. So just to recap, last time we discussed the baseline covariance steering problem, in which you start off with some initial distribution. I'll call it x naught is a Gaussian distribution with some mean and some covariance. And we have this initial distribution, blah, 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 and then we have a bunch of trajectories that come from this initial distribution. And the way we calculate these trajectories are through the linear discrete time dynamical system. So this is our linear system plus bk uk, and then we also have a disturbance, which is what makes the system stochastic. And so we have an initial distribution rather. We have discrete time stochastic linear dynamics, and we also have a terminal distribution. We'll call it xf, is some terminal Gaussian distribution. So it has some mean mu f, and it has some covariance sigma f. And our goal is to design a control sequence uk that minimizes some cost function. And this cost function, we said, was just a quadratic cost function. It was the expected value of just a quadratic cost in terms of the state and in terms of the input. So we want to find this controller that steers our whole distribution from this initial Gaussian distribution to this terminal Gaussian distribution, such that at the same time it minimizes this quadratic cost function. And we found this controller, and we said this controller, the optimal controller, is given by, it could either be full state feedback, full state history feedback, or just the current state history feedback. Well, we've postulated this controller that's made up of two terms. It's made up of an open loop term that steers the mean of the system, and it also has a feedback or closed loop term that steers the deviation of the system. And we did the math, we created this augmented system, we reformulated the dynamics, and we put everything into a convex optimization framework. And once it's in a convex optimization framework, we're able to solve it in MATLAB pretty efficiently. And so this is all nice and well, but what happens when you start adding constraints on the system? Let's say we have a controller. In real life, it cannot produce infinite amount of thrust, for example. It's going to be capped at some values. These are called the saturation values. So if you imagine this to be the axis, let's say this is time and this is control input, then our controller is going to be bounded. So it can saturate, and it could look something like this. But if we don't apply these constraints, let's call this u max and u min, if we don't apply these constraints, then our optimal solution, let me use a different color here, our optimal solution can look wildly different. It can even look something like this, for example, that it goes above the saturation value, and that's no bueno. This is no bueno. Because you can imagine in real life, you're firing the thrusters above their maximum value, it has too much stresses on them, they blow up, and that's it. Millions of dollars gone. I'm exaggerating, of course, but we have to take into account constraints. Additionally, there could be path constraints on the vehicle as well. Let's say it has to stay within these yellow lines. This is its state space, what's called, and I denote it by capital X. Let's say the state has to stay within these boundaries. Well, then our optimal solution is no longer valid, because as you can see, all of these trajectories, they fall outside of the region. So we need to enforce constraints on our system. So just a bit of motivation here. Motivation. In real life problems, right, we have to enforce constraints. And this is critical, if we cannot even do this simple task, then there's no point of doing path planning or decision making under uncertainty. It's all useless. And the reason why is because there's so many examples in real life where we have constraints. I only mentioned a couple right now, but they're pretty important. First of all is control saturation, right? Another one is, we can say, sensor, how should I say it? Sensor regions. So for example, let's say you have a spacecraft, right? This is my ugly spacecraft. But this is my spacecraft and it has a camera on it. And let's say this spacecraft is trying to dock with another spacecraft, right? You have two spacecrafts and they have to dock with each other. It's a classic rendezvous problem. But the problem is that this spacecraft, okay, it has a camera. Let's make a little eyeball here. But this camera only has a certain line of sight that it can see with some angle theta. So it can only see in this line of sight. So when we're, as control engineers, as GNC people, we have to design the controller such that the first spacecraft, also called the chaser spacecraft, is within the line of sight of the target, right? Has to be within this cone at all time steps. And this is the target spacecraft. And so in this case, our state space region that the spacecraft has to fly in, it's actually a cone. And we're going to get into this probably in the next video. But there's two different types of state space regions or constraint spaces that we want to look at. So let's say, what kind of constraints? And so one of them is what are known as polytope, and the second are cones. And so these are the two main classes right now that people are doing research on, and so I want to mention them both. This one is relatively new, and I will link a paper in this video that goes over how to deal with cone constraints. But we're going to focus on the polytope case for now, because it's the most, that's what people work with the most, and it's also much easier in terms of the math. So what is a polytope? Polytope, schmolytope. Well, what actually is it? Well, I'm going to write down the definition first of a polytope. I'll call it XP. And a polytope is defined, there are two different ways to define it. It has two different interpretations. But the one we're going to go with is called the half-space interpretation. And the reason why it's called that is because we write the polytope as an intersection, a finite intersection, from 1 to, let's say, nx of half-spaces. And what is a half-space? Well, a half-space is just defined to be a linear inequality. So you see this linear inequality, alpha j transpose x is less than beta j. That's what is known as a half-space. And why is it called a half-space? Well, I'll show you pictorially. Let's say we're in the xy plane, and our state vector is just two-dimensional. So it's some x1, x2. And let's say this is the x2 axis, and this is the x1 axis. Well, okay, what are these half-planes? What do they look like? Well, they look something like this. You can imagine this is one half-plane, and we'll say it's alpha 1 transpose x is less than beta 1. That's that whole set there. From this line all the way down. That's a half-space. Another half-space could be something like this. Could be something like this. This is the boundary, and then everything to the left is the half-space. So this could be, let's say, the set alpha 2 transpose x is less than beta 2. And you can have several of these. You can have who knows how many. This could be another one, and then you can have everything above this guy. This is, let's say, the set alpha 3 transpose x is less than beta 3. And so when you take the intersection of all this, I know it's kind of sloppy over here. Oops. But let me redraw it. If you take the intersection of everything, what ends up happening is you have this line here, for example. You have this line here, for example. I drew that kind of bad. You have this line here, and then maybe you have this line here. And you see what happens in the end is that you get this region. It's a closed region in Rn, since x is in Rn in general. Here it's in R2. So this would be a region in R2. So since X is in R2, then our state space region is going to be a subset of R2, right? Because it's just this triangular region here. And it's going to be a closed region, it's going to be compact, it has favorable properties, and that's why we like working with half spaces, is because they can be defined in terms of linear inequalities. The reason why I say it's linear is because let's say X is in Rn, is just in general Rn, then this guy, alpha j transpose X less than beta j, is going to look something like this. It's going to be like alpha j 1 x1 plus alpha j2 x2 plus alpha j and x. Alpha j lowercase n xn is less than beta j. So it's going to look something like this. And this is just a linear combination, right? This is just a linear combination. So that's why we like half planes, is because we can approximate things pretty well with half planes, literally to n dimensions. You can do it in any dimension. And they're linear inequality constraints. So they're favorable for our purposes because we can work with them easier. This is completely contrasted to a cone, because a cone has the following definition. A cone is defined as the set X such that AX plus B, the norm of AX plus B, is less than CX plus D. And you see we're taking the 2 norm here. And so this becomes a quadratic state space. It's no longer linear. And so cone constraints are much harder to work with, but we've actually shown in a previous paper that it's a pretty recent paper actually, that we can turn the cone constraints into linear constraints. There is an approximation associated with that, but there is, just so you know, there is some theory to back this up and to reformulate cone constraints. But that's besides the point. Right now we're just looking at polytopes that are defined to be the intersection of half spaces or linear inequalities. Okay, so that's the type of constraints we're working with, but what are chance constraints? That must be the question of the hour. What are chance constraints? And to answer this question, I want to remind you of something from before. And what I want to remind is that we're dealing with stochastic systems here, right? Remember we had this diagram that we start off with some initial distribution, and we have all these trajectories, blah, 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 to go to this final distribution, eta and f. So initial distribution, and then we have the stochastic system that gives us the terminal distribution. Okay, but we have a stochastic system. That's the key word here. Our system is stochastic, which means that it's not going to follow the same trajectory every single time. There's noise acting on the system. And so it's going to take a variety of trajectories. It's going to take a whole distribution of trajectories if you actually sampled it. Like, let's say I did 100 or even 1,000 Monte Carlo trials, I'll have a whole distribution of trajectories. And so in that regard, if we have hard boundaries, like let's say that this is our constraint region, right? This little box here, let's say. This is our state space region. And we have to stay inside of this yellow box. It's actually a trapezoid, or whatever. Since we have a stochastic system, since system is stochastic, then it's very, very difficult to enforce exact constraints. So it's difficult to enforce what are known as hard constraints. Hard constraints. And hard constraints just means that we have the constraints that xk, the state at time k, has to remain within this polytope for all k equals 0 to n. Well, technically it should be from 1 to n. So these are what are called hard constraints because they have to be satisfied at every time step, no matter what. No matter what. The problem is our disturbances are unbounded, right? Think about the case of a Gaussian disturbance. It's Gaussian distributed, right? And these tails go to negative infinity and positive infinity. So technically speaking, we can actually get a disturbance that's extremely high. Even though the probability is really small, it's not zero. It might be, probability might be 0.0001, but it's not zero. So that's what I mean by unbounded disturbances. And when you have these unbounded disturbances, it's very difficult to enforce exact constraints. Because you can have a scenario where you get a crazy amount of noise, and then it just cannot it cannot stay in that trapezoid anymore. So that's why instead of enforcing deterministic constraints or hard constraints, instead we enforce probabilistic constraints. And these are just saying, probabilistic constraints are just saying, okay, I understand we cannot enforce exact constraints, so instead let's say that the probability that X is in the state space, let's say that the probability has to be greater than some 1 minus delta. And delta is usually a small number. So let's say, for example, delta is equal to 0.01. That's 1% right there. Delta is equal to 0.01. Then what this is saying is that the probability that I'm staying in the state space, that I'm staying in this trapezoid, is greater than or equal to 99%. So instead of enforcing hard constraints saying that I have to remain in the state space 100% of the time, all the time, instead of saying that, because it's difficult since we have stochastic systems with unbounded noise, instead we say, okay, I'm just going to enforce that the probability that the state remains inside the state space is greater than 99%, or 95%, or 90%. This is a design variable that you can choose, depending on how conservative or loose you want it to be. If you have a really safety critical mission, then delta would be really small, because you want to stay inside the state space, and you cannot, the probability that you violated should be very small. But if you don't really care, then you can make delta higher, which would lower the probability. So the main point is that since we have disturbances acting on our system that can be unbounded, then it's very difficult to enforce hard constraints, and so as a result we enforce these probabilistic constraints, which are also known as chance constraints. Okay, and I just want to make a quick caveat here and say that there has been work done on hard constraints as well. But the way to solve this problem is much different, and it's a little harder, to be honest, than what we're going to be dealing with here. But there is work on it, even though. Actually, one paper is by Kazuhide Okamoto, and he worked in our group as well, and just look up hard input constraints. That's the paper where he talks about that. And the way he solves the problem is to use what are known as saturation functions. But again, it's more complicated than what we need to be dealing with here. So we're just dealing with chance constraints, probabilistic constraints that limit the probability of violating the constraints at every time step. Okay. So we have these constraints. Hopefully I've convinced you that we need to deal with probabilistic constraints or chance constraints, but these are what it becomes. This is what the constraints become at the end of the day. The probability, so just to read this statement here, just to read this equation, it states that the probability that the state at time k is inside the state space, the polytope state space, the probability that this happens has to be greater than 1 minus delta. And actually, I've made an inaccuracy here. I should write that the probability, that the state space and this, I'm going to put this logical AND operator. So this is even more accurate. This is more accurate because this says that the probability that the state stays inside the state space over the whole horizon. So this AND logical operator means over the whole horizon. Over the whole horizon. So this means from k equals 1, yes, to k equals n. So the probability that the rocket stays in this cone or in this polytope over the whole horizon has to be greater than 1 minus delta. And when you write it like this, these constraints, these chance constraints, are called joint chance constraints. Because joint means that you're essentially summing up over every time step. They're a joint chance constraint because we're interested in the probability of violating over the whole horizon. There's another type of chance constraints called individual chance constraint. So individual chance constraints. And these only care about the probability that the state remains inside the polytope at one time step only. Only at time step k. And usually when we write individual chance constraints, we say that they have to be greater than 1 minus lowercase delta. Okay? So this is a very fundamental distinction that's very important. In our formalism, we use joint chance constraints because they're more natural to deal with. Let's say that you're a designer, you want to design a trajectory, right? And you have some kind of a region in three-dimensional space that you don't want the vehicle to exit from. You want it to stay inside this three-dimensional region of space. Naturally, you would want to stay in this region over the whole horizon, and you want to penalize it over the whole horizon. You don't care that it's 5% probability at time step 1, 1% probability at time step 2. You only care about the probability of violating over the whole horizon, which is why it's more natural to deal with this capital delta than this lowercase delta. We'll see in a couple minutes that in order to solve the joint chance constraint problem, we actually end up going to individual chance constraints. And it's kind of funny, but it's a necessary thing we have to do in order to solve this problem. Because take a look at these constraints. Take a look at these joint chance constraints here. It's not clear what to do with them. Like, we have these constraints, okay, but how do we actually put them into a convex optimization framework? This is not clear at all. So that's what we're going to get into now. We have these chance constraints and we want to do something with them. So, step number 1. We have to plug in our polytope. And remember, our polytope was defined to be an intersection, not a zero, an intersection over half planes, right? And these were our half planes. Alpha x is less than beta. Okay, so let's plug this in. And so the probability that the state remains inside the polytope over the whole horizon, it's the same thing as the probability from k equals 1 to n that alpha j transpose x k is less than or equal to beta j. It's literally the same thing. These two are equivalent. The reason why is because all I've done to get from the left-hand side to the right-hand side, I just plugged in the polytope. If the state satisfies this inequality, that means it's in one of the sides of the polytope. And if this is satisfied for all n, for all time steps, then it's in the polytope for all time steps. It's as simple as that. So this has to be less than or equal to 1 minus delta. And now we have to say for all time steps, for all sides of the polytope. For all j from 1 to nx. Okay? So all I've done here, I took the definition of a polytope, I plugged it in, and I'm saying now that in order to satisfy this for all time steps here, I can satisfy it for all sides as well. So for example, this can be j equals 1, j equals 2, j equals 3, j equals 4. If it's inside all of these, then it must be inside the polytope. That's it. Okay, so we got this. Now what? We still have this pesky AND operator here. You can think of this AND operator as like a logical. So for example, let's say I have a proposition 1, P1, I go to the gym. And then I have another proposition P2, I drink a protein shake. I drink protein shake. What this AND operator is k equals 1 to 2 of pk, that's just P1 and P2, which means I go to gym and I drink shake. So that's what I mean by a logical operator. It kind of says, you say this and this and this and this all the way to time step n. That's why this is called a joint chance constraint again, because we are saying that the probability that it's inside the state space at all time step, at time step 1 and at time step 2 and at time step 3, all the way to time step n. But we can't work with this AND operator. We need to get rid of it. And that's where Boole's inequality comes into play. So Boole's inequality. What is Boole's inequality? Boole's inequality gives us a means to take a joint chance constraint, as we have here, over the whole horizon and break it up into individual chance constraints. So let me just write this down a little more in English. Boole's inequality it turns joint chance constraints to individual chance constraints. And what do I mean by this? In mathematics, it says that, okay, if I have the probability that x over the whole horizon, if I have a joint chance constraint, k equals 1 to n, over the whole horizon, is greater than 1 minus delta. So if I have this joint chance constraint, then Boole's inequality says that, okay, this is satisfied if and only if the individual chance constraints are satisfied, where the risk is delta k. And we have to make sure that the sum from k equals 1 to n of delta k is less than capital delta. So this is the statement of Boole's inequality right here. And let's just go through it real quick. We have the joint chance constraint that limits the probability of violating the constraints over the entire horizon. And delta here is the joint probability of failure, also known as the joint risk. Because risk here, in the sense that we're allocating risk to the problem, we only want it to violate 5% of the time. That will be what's known as our risk level. So delta here is the probability is our risk level over the entire horizon. And what Boole's inequality is saying is, okay, instead of having this joint risk over the entire horizon, we can equivalently have risk at every time step. And so these are what the delta k's are. This is the risk at time step k. And so Boole's inequality is saying, okay, we have, instead of having the joint risk over the whole horizon, we have the risk at every time step, delta k. And the only thing that we have to make sure is that the summation of all the individual risks has to be less than or equal to the total risk. Right? Does that make sense? Because if we assign a total risk of 5% and we split it up over the whole horizon, you better make sure that when you split it up, it's still less than 5%. Right? You can't split it up and have it be 20%. Then that wouldn't work. So Boole's inequality gives us a way to get individual chance constraints, as we have here, but under one extra condition, in that they sum up to be less than the total risk. So hopefully that makes sense. And that is the power of Boole's inequality. Because now this equation here, this inequality, we can actually work with this. And I'll show you exactly how right now. So now we have these individual chance constraints. And the first thing I'm going to do, just the same as last time, I am going to plug in XP, the polytope. I'm going to plug in the polytope. And so this guy, this statement in the probability becomes alpha j transpose xk is less than beta j, right? In order for xk to be inside the polytope, that means that it has to be inside each of the sides, right? It has to remain inside each of the half planes. And it should remain inside all of the half planes. So for all k, for all time steps from 1 to n, and for all half planes from 1 to nx, right? And of course we have, well, now we have, so, sorry, let me explain a little bit more clearly. On the left-hand side here, we're saying that probability that xk is in polytope is greater than or equal to 1 minus delta k, right? This is just a statement of the individual chance constraint. Over here, I'm plugging in the definition of the polytope. However, the polytope has j sides to polytope, right? Remember we had this polytope, and let's say j equals 1 is here, j equals 2, j equals 3, j equals 4, for example. So in order for the state to remain inside the polytope, it's the same thing as saying that the state has to remain within each side of the polytope. And this has to hold for all the sides. And it also has to hold for all time steps. So if you crunch the numbers a little bit, you'll see that this right here, this statement right here, it's actually n times nx constraints. N times nx constraints. Why? Well, because we have n constraints for n time steps, and we also have nx sides of the polytope. So as a result, you multiply the two together and you get n times nx constraints. And you can imagine that, let's say your time horizon is 100 steps, and you have 4 sides. This gives you already 400 constraints, extra constraints. And so it adds up pretty quickly. But just so you know, this is how we go from joint chance constraints to individual chance constraints, and now we're dealing with the individual chance constraints. So, now we have the constraints that the probability that alpha j transpose xk is less than beta j is greater than or equal to 1 minus delta jk. Additionally, we have the constraint from Boole's inequality that the sum over the whole horizon now is going to be a double sum of delta jk is less than or equal to delta. So this is what happens, this is where we are now. The first line here, these are the individual chance constraints, and this one on the bottom is the total risk from Boole's inequality. Okay? Alright, what's the next step? Well, the next step is xk. What do we do about xk? Well, remember from the previous video what we had. We had that we reformulated our problem in terms of the augmented vector x. Remember that? And this augmented vector was the whole history of the state. And so we had that x, capital X, is equal to a x naught plus bu plus dw. Correct? So we can actually plug it in. One more thing to remember is that xk is the same as ek times x. Remember, because this ek matrix isolates the kth state element from capital X. Okay, so let's plug it in. Well, before that, I want to just review something. Remember from last video, we had this reformulation in terms of the augmented dynamics. Taking the mean of this, we get a mu naught plus bu bar. right? Because the expected value of W is equal to 0. It's a zero mean and unit covariance random variable. From last video, remember our controller was k times x tilde plus w. Plus v. Oops. Plus v. Which means that the mean controller is v, and the deviation controller is k times x tilde. This was from last video. So that means that x bar is a mu naught plus curly b times v. Okay. How about the covariance? Sigma xx. Well, the covariance, if you remember from previous video, it was equal to I plus BL times S times I plus BL transpose. I'm not going to go through the derivation again. If you forgot where this came from, just go through the previous video. And remember, this L was this new change of variables from before. New change of variables. Okay? Just if you don't remember. Go back to the previous video. So this is the mean, and this is the covariance. And the dynamics are linear. And this is very important, because since the dynamics are linear, and since the initial condition is a Gaussian distribution, so initial condition is Gaussian plus linear dynamics plus feedback controller, right? Because u tilde is equal to k times x tilde. So all three of these things combined, initial condition is Gaussian, linear dynamics, feedback controller. This all implies that the state, process x, remains Gaussian. I should also mention here that we have Gaussian disturbances too. So we have a Gaussian disturbances, we have a Gaussian initial condition, we have linear dynamics, and we have a linear feedback controller. All of these points, they imply that the state process, it remains Gaussian over time. So if you take like a bunch of trajectories, right? Take a bunch of trajectories and you make a cut at every time step, it's going to be Gaussian distributed. It's going to look something like this. So these should all be Gaussians. Whoops. So at every time step, it's going to stay Gaussian. So k equals 1, k equals 2, k equals 5, all the way to k equals n. The state is going to remain a Gaussian random vector, which means that the state has some mean and some covariance, right? The whole point of Gaussian vectors, which is why we like to use them so much, is that you can completely specify a Gaussian vector, a Gaussian random variable, in terms of its mean and its covariance. You only need the first two moments. These are called moments. The mean is the first moment. The covariance is the second moment. You only need the first two moments of a normally distributed random variable to completely identify it. Okay, that's very important. There are no higher order moments. You just need the mean and you need the covariance. And we've just shown that since we have an initial Gaussian distribution, since all of our noise is Gaussian, since we have linear dynamics and everything, this implies that the state remains Gaussian over time. Which means that if we know the mean of the state and if we know the covariance of the state, we know the whole distribution at every time step. Okay? That's a very important point. And the reason why it's important, let's go back to the chance constraints. We have alpha j transpose xk is less than beta j is greater than or equal to 1 minus delta jk. These are our chance constraints. The first thing I'm going to do, I'm going to rewrite it in terms of the augmented state. So x ek times x. And this just comes from the fact that xk can be written as ek times x, right? I showed this before, like a couple minutes ago. So I just plugged that in, that's all I did for now. But now notice what's going on here. Notice what's going on here. X is a Gaussian random variable. It's a Gaussian. It's a normally distributed random variable. It has a mean x bar. It has a covariance sigma xx. We know everything about it, right? So what this is saying is that it's only asking us to compute the probability that a function of the random variable is less than something. This is literally all it's saying. A function of x is less than beta j. Is greater than 1 minus delta jk. So how do we compute this? What is this? Well, what is it? I can tell you. Hold up. Oh, my thing is bugging out. Sorry about that. I don't really know what happened there. But anyways, we're still trying to figure out how to find this probability. The probability that a function of a random variable, the function of a Gaussian random variable, is less than or equal to some value. And to solve this problem, I want to, let's go back to the basics real quick. The basics of random variables. Basics. So let's say I have a random variable x. It's just a one-dimensional random variable. And it's a normal random variable. It has a mean mu and a covariance sigma. It has some probability density rho of x, right? And this probability density is just a what was it again for a normal random variable? 1 over 2 pi sigma squared, square root of 2 pi sigma squared. Instead of covariance, I'm just going to write variance because it's one-dimensional. So we have a one-dimensional random variable. It has a mean mu, it has a variance sigma squared, and its probability density function, which I'm going to write as rho, is equal to 1 over square root of 2 pi sigma squared times exponential of negative x minus mu squared over 2 sigma squared. This is the probability density of the random variable. And if I want to ask the question, what is the probability that x is less than some number? Let's call it gamma. How do we find this probability? Well, there's a bunch of ways to do it, obviously. We can do it from the density function rho, because for a Gaussian distribution, the density function will have this bell shape, right? And if we want to find the probability that x is less than gamma, let's say this is gamma, then all we have to do is take the integral over the probability density function, right? This is just standard basic probability theory. If you want to find the probability that a random variable is less than gamma, that's the same as taking the integral from negative infinity to gamma of the probability density function. Right? Very simple stuff. Also, I can write this in terms of the cumulative distribution function f. So this is also equivalent to f of gamma. The cumulative distribution function is literally the probability that the random variable is less than gamma. So, what if we wanted to use, instead of this cumulative distribution function, what if I wanted to use the standard normal cumulative distribution function? So phi is the standard normal CDF. And what do I mean by standard normal? Well, I'll tell you. If the random variable has a mean mu and a covariance sigma, then this would be an off-centered random variable, Gaussian. But if I have a random variable y that has a mean 0 and a covariance of 1, then this would be standard normal. So this is just a normal random variable, while this is a standard normal random variable. And standard just means that it has a 0 mean and unit covariance. That's all it means. And in order to get y from x, you have to do a transformation. And what is this transformation? Well, y is simply x minus mu over sigma squared over sigma. Sorry. This is the transformation. So this is the transformation from just a regular random variable to standard normal. So it's from a normal random variable to a standard normal random variable. That's how we compute the transformation. So if I wanted to find the probability that x is less than gamma, I can surely compute it as the cumulative distribution function at gamma. But I can also compute it in terms of the standard normal. So this is the standard normal CDF. But in this case, it would be gamma minus x bar over sigma x, using this change of variable. Okay? And so this would just be phi of gamma minus mu over sigma. Okay? So just to make sure we're on the same page, x is just is a normal random variable. It has a mean mu. It has a variance, let's say sigma. Sigma squared is the variance. In order to compute the probability that x is less than or equal to gamma, we can either compute it through the CDF of x. So this is the CDF of x. Or we can compute it in terms of the CDF of a standard normal variable, CDF of y. But we have to use this change of variables if we want to do that. And the reason why we want to use phi is because it's very easy to compute it in MATLAB, or just in general. The values of phi can be found from any lookup table, right? It's already been documented. Everybody knows the cumulative distribution function of a standard normal random variable. It's like, the reason why we use it is because it's standardized. It's in MATLAB as a nice function, inverse CDF, or just standard normal CDF. You can compute the inverse of it, and it's just nice to work with. So that's why we want to express everything in terms of the standard normal CDF. Okay? So now back to the problem at hand. We want to find the probability that some function of x is less than beta j, where this function of x is given by alpha j transpose ekx. Right? This was our function of x, right here, f of x. Okay, how do we compute that? Well, just take the analogy from here. The probability that f of x is less than gamma, right, is equal to the standard normal CDF of gamma minus mu. What is mu? Well, mu is the expected value divided by sigma. Sigma is the standard deviation, also known as the square root of the covariance. There it is. So we have to compute the expected value of f, and we also have to compute the covariance of f. Okay. F bar. What is f bar? F bar is just the expected value of f, and f is this guy right here. So we take the expected value, and we get ek times x bar. But you remember x bar is just a times mu naught plus b times v. Aha, we got f bar. Easy peasy. Sigma f. Sigma f, you do the same procedure. We know what f of x is. I'm not going to do it here, but you can do it as an exercise. I know already, by just looking at it, that the covariance is going to look like this. It's going to have this form right here. And we know what sigma xx is. I'll just write it again real quick. I plus bl times s times I plus bl transpose times ek transpose times alpha j. Okay, we got the mean f bar, we got the covariance sigma f. So now we just plug it in. The probability that f of x is less than gamma Well, it's not gamma, right? It's beta j. Beta j is the same as gamma. So the probability that f of x is less than beta j is equal to the CDF evaluated, that's an ugly CDF, the CDF evaluated at, what's gamma? Beta j, minus f bar. What is f bar? Alpha j transpose ek a mu naught plus bv divided by, divided by sigma f to the 1/2 power. Okay, so alpha j transpose ek I plus bl, this guy, this whole mess, and then square root of that whole thing. Trying to write it as neatly as possible. There we go. That's the probability. So just to recap, we had the probability that a function of the random variable is less than beta. We chose to express this probability in terms of the standard normal CDF, because we can easily compute that. And now, remember from the chance constraints, we had that this probability has to be greater than or equal to 1 minus delta jk. Aha! So look what's happened now. We've turned this probability into an expression in terms of v and l. And v and l are our optimization variables. So now we're very close to solving this chance constraint problem. Let's take the inverse, CDF of both sides. Take inverse CDF. And why do I do this? Well, I'll tell you, take inverse CDF because the inverse of the inverse CDF of the CDF is equal to the identity, right? It's just equal to 1. So if I take the inverse, then that thing will go away, and I will just be left with this guy. I'll be left with the term inside of the brackets, divided by this whole guy. Don't forget the square root. And then this is greater than or equal to the inverse CDF of 1 minus delta jk. Okay, so this is where we're at now. One more thing I want to point out to simplify everything is we have a square root of some kind of norm, right? And why do I say this is some kind of norm? Well, think about the 2 norm. Let's say I have a function, let's say I have a random, like just any vector z, and I take the norm of it squared, the 2 norm squared. This is the same thing as z transpose times z. It's just a dot product. And if you haven't seen this before, then don't worry. This is just the 2 norm squared. It's just the Euclidean norm, right? It's just z1 squared plus dot 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 plus zn squared. Well, I'll say zn squared. It's just the Euclidean distance. That's the 2 norm, is the Euclidean distance squared. Okay? And now look here. We have this guy and this guy. And they're basically transposes of each other. And take a look at this even more. Let me write it like this. I hate when it does that. Let me write it like this. Aha. So now look what's going on. This and this, let's call it capital Z, capital Z. This is just a 2 norm. This guy, this right-hand side, and the left-hand side are literally the same thing, except they're transposes of each other. Okay? So, I have a square root of Z transpose Z, which is the same thing as square root of the 2 norm of Z squared. When you take the square root of something squared, they cancel out, and I'm just left with the 2 norm of z. There we go. So I can rewrite the chance constraints as the following. Divided by, now instead of the square root has canceled out with the squared, so we're just left with the norm of s to the 1/2. By the way, s to the 1/2, s to the 1/2, this can be found through what's called a Cholesky decomposition. A Cholesky decomposition, if s is positive definite, it gives you the square root of the matrix. I don't really want to get too much into it technically, but that's kind of what's going on here. You can find the square root of the matrix because from this Cholesky decomposition. And the square root of the matrix has the property that V transpose V is equal to S, where V is S to the 1/2. Okay? It's just the square root of the matrix in a sense, it's the square root of the matrix. Okay, whatever. So we have this 2 norm, S to the 1/2, I plus BL transpose, EK transpose alpha J. And this is all greater than or equal to the inverse CDF. Okay, a couple more things I want to do. I want to multiply this on that side. So I'll get boom. Just a little bit of algebra, but we're almost done. Okay. So, last step, I'm going to move this to the other side. So at the end of the day, what we get is plus this whole guy, and this is all less than or equal to beta j. And this holds for all k for the whole time horizon and over all half planes. This is it. We have one more constraint from Boole's inequality, and that's it. Okay, so this is the final product of everything we've done. We've started with these joint chance constraints, and then through Boole's inequality, we were able to turn the joint chance constraints into individual chance constraints. From the individual chance constraints, we saw that, okay, we have a random variable x, and since the noise is random, since the noise is Gaussian distributed, since the initial condition is Gaussian, and since the controller is state feedback, that means that the state is going to remain a Gaussian random variable throughout the whole horizon. Since it remains a Gaussian random variable throughout the whole horizon, we can write this probability in terms of a cumulative distribution function, namely the standard normal cumulative distribution function. And through that, we get these constraints here, 1 and 2. And the beautiful part is that the constraints, these constraints, they're what are known as cone constraints. More specifically, they're called second order cone constraints. And the reason why are they called cone constraints? Well, I mentioned this briefly, but a cone can be written as ax plus b, 2 norm, is less than cx plus d. This is the equation of a general convex cone. So this is a convex cone. Okay? And look what we have. We have some 2 norm, right? Some 2 norm with our decision variable is less than or equal to cx plus d. This would be our d, and this would be our cx, right? Because this is our decision variable. So this is a second order cone constraint. It's second order because we have the 2 norm here, And it's a cone constraint because it has the form of a convex cone. And this is actually perfect because cone constraints can be formulated. A semi-definite program solver can actually solve cone constraints. It can take in these type of constraints because they're convex. And this all comes back to this concept of convex optimization. We want to reformulate our problem just as we did in the last video in terms of some convex optimization problem, specifically a semi-definite program. And a semi-definite program, it can take cone constraints, it can take second-order cone constraints, it can take linear constraints, it can take linear matrix inequalities. So we try to reformulate all of our constraints in terms of these convex constraints so that our solver can actually solve the problem. And that's exactly what we did here. We've reformulated these probabilistic constraints as deterministic constraints and specifically as cone constraints. And so we put this so this goes into our optimizer as cone constraints. And the optimizer, let's call it MOSEC, that's the optimizer we use. It optimizes the cost and spits out an optimal L star and an optimal V star. These are the controllers, from which we get the optimal control U star. Right? This is kind of how it works. So in addition to all the constraints that we had from the last video, we now have an additional constraints from these chance constraints. And remember, there are n times nx of these constraints. So we're adding in more complexity into the problem, but we're doing it in a smart way such that the solver can actually still solve the problem. If you give the solver these probabilities, it won't know what to do with it because it doesn't know what a probability is. But if you give it a cone constraint, then it actually can work with it. It can solve the problem subject to those cone constraints. And these constraints right here, they're just linear constraints. It's just a summation, right? So we're going to have like delta 0, 0 plus delta ij plus delta nx. It's just going to be a big, big sum. It's also all less than delta. So these are just linear constraints. So, in summary, we've went through the motivation of why we need chance constraints. We have an unbounded disturbances on the system, so it's very hard to enforce deterministic constraints. As a result, we use chance constraints to limit the probability of violating the constraints over the whole horizon. These are what are known as joint chance constraints. We used Boole's inequality that says you can decouple, it's not decouple, you can decompose a joint chance constraint into individual chance constraints. Once we have these individual chance constraints already, we know that all of our noise and our initial condition is Gaussian, so the state is going to remain Gaussian over the whole horizon, which means we can reformulate our chance constraints in terms of second order cone constraints. And this gets plugged into the optimizer, and then the optimizer solves it and gives us a beautiful solution. So that's it. We've went through how to reformulate polytope chance constraints. If you're curious about cone chance constraints, it's very similar. I'll attach the paper in the description. But that's about it for chance constraint optimization. Yeah, thanks for watching.